Okay, so the first thing I want to tell you is that your break homework is in, um, I'll distribute it to you, but it's under review materials in the OneNote notebook. The whole thing is there. So if you're taking your notebook, or if you're taking your computer home with you for winter break, you can do it in your notebook. If you want to print it out, you can print it out. It's quite a decent stack. There are 39 multiple choice questions, and I think 4 actual exam part 2 questions. Okay? The absolute worst thing you can do is do all of this before winter break, or go home the first day of winter break and do it all. That's not the point. The point of the winter break homework is that I cannot have you not think about physics for 2, 2.5, 3 weeks. If you do that, it's a disaster, because then we have to cram everything back into your head when you come back. The second worst thing you can do is save it and do it all the night before classes start again, but then at least you crammed it back into your head and I didn't have to. The way this is designed is that you do a couple problems a day, every day. You go away with your family for a day or two, don't worry about it, leave it at home. You're traveling for 24 hours straight and changing time zones, it's okay, put it aside for a couple days. But you need to spend time doing this, but do it in, 10, 15, 20, 30-minute chunks every day. If you're doing it in 30-minute chunks, you could probably do every other day. You can use your notes to answer these. You can use your textbook to answer these. Please do not use the internet, because looking up the answer is not going to help anybody, because it's not graded. This isn't about getting the right answer. It's about not forgetting everything that we have spent the last 4 months learning. Okay? And then we will go over it when we come back. Okay? And you can ask questions, and you will have specific questions. And I encourage you to write notes in the margins. And I encourage you to work on this so that when you come back, you know why you did a certain problem wrong. Okay? Or whatever. All right, so are there questions on this? Okay, everybody good? I will distribute it, but you can go up to class content and its review materials, and it says winter break review. Okay? All right, so now that I have yelled at Casey, I want to review just briefly what we were talking about with the elastic potential energy. Okay? So the change in elastic potential energy, and remember that whenever we're talking about potential energy, we're always talking about a change in configuration, okay? A change in the arrangements, the placement of the particles or the objects that we're dealing with from one situation to another. So when we're talking about the elastic potential energy, we're talking about stretching the spring from one distance to another distance, okay? And stretching and compressing is really interchangeable. It doesn't matter. You need to know that, and you need to call it plus or minus, but it's not really going to affect what you get when you do the change in potential energy. So that formula was 1/2 K xf squared minus 1/2 K xi squared. And what's the K? The K is the spring constant, okay? And we measure xf and xi from the relaxed length or the natural length of the spring. And as we talked about this when we talked about it 2 days ago, because yesterday was lab, we talked about how sometimes you can measure all of the potential energies with respect to that x equals 0 position, okay? So if I measure with respect to x equals 0, at the relaxed length, then I can talk about the spring having an amount of energy that's 1/2 kx squared. Okay, but it's implied that I'm comparing the amount of potential energy in the spring at x with the amount of potential energy in the spring at x equals 0. Okay, makes sense? X is still going to be measured from the relaxed length of the spring, excuse me. It's just that I've put the added thing here that the relaxed length of the spring is going to be where x is equal to 0. Okay? So I just want to do a real quick kind of plug and chug example to get you used to the formula, and then we're going to do something else that's going to build us into conservation of mechanical energy. Okay? Everybody got what they need? Priya, you good? Okay. All right. So let's do sample problem 12. Sure, that would be great, Priya, if you read it. Okay, so let's just talk about what we're talking about here in part A. All right, so we're going to assume that the second stretch is greater than the first. We don't have to, it would work, but that's just the way I'm going to draw it. Okay. It doesn't matter. Didn't you bring, I thought you brought that up, Zoe, when you were doing something on the homework, as everybody else will find too. Okay. So I'm just going to draw here where x is equal to 0 for my natural length. And so I'm going to have the end of my spring, and it just hangs here. So this is the natural or relaxed length. Okay. And then initially, we compress the spring into some x0. And then we're going to compress it even farther to some x. So if I want to find the change in the elastic potential energy, it's going to be whatever the potential energy is at that final position minus the elastic potential energy at the initial position. So what's my formula again for elastic potential energy? No. I just want to find elastic potential energy. What's that formula that we came up with? I had it on the last screen. Yeah, 1/2 kx squared. So this is going to give me 1/2 k x final squared minus 1/2 k x initial squared. So that gives me 1/2 k. What's my x final? But it has a specific letter, symbol assigned to it. What? Nope. In my problem, it's x. Because that's the final compression of the spring. So it's going to be 1/2 kx squared minus 1/2 kx naught squared. Okay. All right, like I said, this part is really just practice with the formulas. Okay, are we good? All right, somebody read us part B. Okay, so again, we can make some pictures here, and here's going to be x equals 0, and our spring at its natural length. And I want to compare two situations. One where my spring is compressed to x naught, and one where my spring is stretched to x naught. So if I let positive be to the left, then when I stretch my spring, that's a negative x naught. Okay. So again, if I want to find the change in elastic potential energy, it's the final elastic potential energy minus the initial elastic potential energy. And so again, I'm using my formula, 1/2 k xf squared minus 1/2 k xi squared. What's my final position? Well, my final position, if I call this my final position, it's negative x naught. And then what's my initial position? X naught. Well, yeah, pretty much, because this is going to give me 1/2 k x naught squared minus 1/2 k x naught squared. So my change in elastic potential energy is 0. So it really doesn't matter. It may matter to the problem. It may matter to other things. But as far as potential energy is concerned, there's really not a difference between stretching and compressing the spring by the same amount. The same amount of energy is stored in there, whether I stretch it 3 centimeters or compress it 3 centimeters. Okay, kind of wacky, but true. All right, we good? Okay, let's see if we can get through this first problem here. I don't know if we'll get through everything I want to do. All right, so page 202, number 7. If somebody wants to read it for us, I'll tell you when to stop. let's stop there for a minute. So again, this is a problem where I don't really care what the numbers are because I think it's a lot easier to see things if we're just looking at symbols. So basically I've got my rod is pulled out here, some angle theta. As you may remember from freshman year, when you've got a mass on the end of a a mass on the end of a rod or a string like this for a pendulum, we call it a bob. I don't know why, but we do. Maybe, but I don't really know what it would have to do with your hair that way, or one's hair that way. Okay, and the length is L. And then what's going to happen is it's going to be released, and it's going to swing down to here. Okay? And we want to know how much work the gravitational force does on the object and what the change in potential energy is going to be. Okay, makes sense? Okay. What kind of a force is the gravitational force? Conservative or non-conservative? Conservative. So if the gravitational force is conservative, what does that mean about calculating the work? Zoe? I wouldn't say it that way. I would say it doesn't matter what path it takes, okay? As long as we get the end point and the initial point divided by the same thing. So since I'm talking about the gravitational force, and which way does the gravitational force point? Down, okay? So the gravitational force is going to point down. Then I only care about the vertical distance here, right? Because what's work equal to for a constant force, such as the gravitational force? What's work equal to? Let's go more general. What's work equal to? F dot D. Okay, so only the parts of the force and the distance that are parallel are going to contribute to the work. So that means that I only care about that vertical height h that the ball moves. I don't care what it does in that horizontal direction. I don't care that it makes this arc, because I'm only going to have that vertical change in direction that's parallel to my gravitational force contribute to the work. Okay? But the question is, how do I find h? So let's find h. What I am about to teach you, or point out to you because it's there, is what I would call a life skill for you, because you are physics students. It will come up in other places. You will need it again. You will do another problem, and you'll say, but I don't know how to find that. And I'll say, yeah, you do, because we did this. Remember when we found h? And you'll still look at me funny. And I'll point it out in your notes, and you'll be, oh, yeah, that's what I have to do. Okay? So it's a way of thinking about this. So here's my mass at its lowest height. Okay? And here's my mass where it starts. So this is this distance h that I'm looking for. Okay? So what's this length here? Well, it's L. Okay. And then what's this length here? L. If I could figure out what this is, I could add it to h, and it would be equal to L, right? And I happen to know that angle is theta. It is in fact a right triangle. So how do I get this side over here? What's it going to be equal to in terms of L? I want to find this piece right here. Because when I add that piece to H, I get L. No, I don't want to use numbers at all in this problem. Yeah, but I'm trying to find H, so you can't tell me what that is in terms of H. I want it in terms of the right triangle that you pointed out. Let's review Princess Sakatoa.
L sine theta.
No. Cosine theta is adjacent over hypotenuse.
It is cosine. I was looking at
That I marked with a bracket and then further drew over again. Yeah, that's the side I'm looking for. Okay? Yeah, it is. Okay. So, as it has been pointed out, this whole distance, which is L, is equal to the side of that triangle plus H. So H, no. H is going to be L times 1 minus cosine theta. I brought this term over, and then I factored out an L. Okay. All right. We good? We got it? Okay. So part A was to find the work done by the gravitational force. And the work done by the gravitational force is going to be what? mgd cosine phi? Okay. So I've got my mg. What's my d? What distance has it moved? H. And what's the angle between D and FG? It's not theta, because remember here was my FG, here's my H, it's 0. Okay, so that's going to be cosine 0, and the cosine of 0 is 1. So the work done is going to be mg, and now I'm going to substitute in for h, so that's going to be L times 1 minus cosine theta. Okay. What does part B want? The change in potential energy. And change in potential energy is equal to what? The negative work. I could just make the other one negative, which is going to give me mgl cosine theta minus 1. Think about it before you ask me. Right? I just distributed that negative 1 through the parentheses and flipped them. You know I don't like negative signs in front because you never know if they're really there or not, or if they're a flick of the pencil. Okay? You good? You with me? All right, what does part C ask us for? Somebody read it, please. Okay. So again, we'll just draw the picture here. So we've got UG is equal to 0 down there. So this means that our U final is going to be equal to 0, right? Because that's where the ball ends. And delta U is U final minus U initial. U initial is up there where the ball starts. Yep, and then I'm going to substitute in, yep, the delta U is mgl. Cosine theta minus 1 is negative ui. I'm going to multiply through by that negative 1 and get mgl 1 minus cosine theta. Okay, we good? We got it? All right then. How about part D? What does part D say, please? Okay, so it says, do the magnitudes of the answers to A through C. So in A, we found the work. In B, we found the change in potential energy. And in C, we found the initial potential energy value. Are these values going to increase, decrease, or stay the same if theta is increased? Okay, and let's just recap here. So the work was mgl 1 minus cosine theta. The delta U was mgl cosine theta minus 1, and ui was mgl 1 minus cosine theta, just so I can point. Okay. No, theta, and that's why I very specifically used when I did, where is it? Whoa. That's why here when I use the angle in between H and FG, I very specifically chose phi because theta is the angle that we're pulling the pendulum out to. That's okay. All right. So basically what I'm going to do is pull the pendulum out farther. So what do you think is going to happen if I pull the pendulum out farther? What's going to happen to the work? Well, let's look at it this way. What's going to happen to the change in potential energy if I pull the pendulum out so that it's higher off the ground? It's going to increase. Okay? It's going to get more negative. So I don't really know how we want to do increase, decrease, but the amount is going to get bigger. Because what's going to happen to that UI if I pull it up higher? It's going to get bigger, it's going to increase. So if the magnitude of delta U increases, what's going to happen to the work? Well, it's a magnitude, so that's where this whole negative sign makes what does increase, decrease mean. I think increase, decrease stays the same, has to do with what the magnitude is, because the magnitude will get bigger. But it's a weird use of words. And that's kind of the physics way of looking at it, but we can look at it a math way too. If theta increases, what happens to cosine theta? It'll decrease, right? Because the cosine of 0 is 1, but the cosine of 90 is 0. So as theta gets bigger, cosine theta decreases. So what happens to 1 minus cosine theta? Is that going to increase or decrease? What, Sari? Increase. Because I'm taking 1 and I'm subtracting a smaller and a smaller number. So if 1 minus cosine theta is going to increase, then the work is going to increase and the initial potential energy is going to increase. And if we kind of took the absolute value here, that change in potential energy is going to increase in terms of its magnitude. Okay? All right, I think we will end it here and we'll pick up on Monday, because tomorrow is drop day, with conservation of mechanical energy and do a few more problems. Please check the portal, though, as you go to see if you need to do some more reading for Monday. Chances are you will need to. Okay? Thanks, guys.